Welcome back to G Fun Facts Online. Today we are diving straight into arguably the most complex and intricate architecture in the known universe, the human brain. We are talking about a staggering network of 86 billion neurons and over 100 trillion synapses firing constantly to create your consciousness. Yet, for all its structural majesty and unparalleled processing power, the brain is acutely vulnerable to microscopic errors in its own molecular machinery. Chief among these devastating errors is Alzheimer's disease. This is an insidious neurodegenerative disorder that systematically dismantles a person's memory, cognition, and ultimately, their very identity. For over a century, scientists have been trying to map out exactly how this destruction happens. It all started back in 1906, when Dr. Alois Alzheimer first peered through a microscope and observed strange plaques and tangles in a patient's brain. Since that moment, the entire field of neurobiology has heavily relied on chemical stains and dyes to map out this pathology. But right now, a quiet revolution is completely rewriting the rules of how we study the brain. Driven by massive breakthroughs in optics, quantum physics, and artificial intelligence, researchers are finally abandoning the dyes, the radioactive tracers, and the fluorescent tags. Welcome to the era of label-free neuroimaging, a paradigm shift that is allowing us to map the molecular architecture of Alzheimer's disease in its pure, unaltered native state. To truly appreciate the magnitude of this shift, we first need to understand something called the observer effect in biological imaging. For decades, the absolute gold standard for diagnosing and studying Alzheimer's disease at the tissue level has been histological staining using exogenous reagents. What this means is that pathologists utilize fluorescent dyes like theoflavin S and Congo red, or complex cocktails containing targeted antibodies, to basically force the brain's hidden pathology to reveal itself under a microscope. While these methods have obviously been foundational to modern medicine, they come with a profound scientific cost. When you introduce exogenous dyes into a tissue sample, they can induce unspecific binding. This creates false positive signals or uneven labeling, which can easily mislead researchers. Think of it like trying to study the incredibly delicate mechanics of a Swiss watch by pouring thick fluorescent paint directly into the gears. The very act of attaching a bulky fluorophore to a delicate lipid or protein molecule can alter its natural shape, obscure its interactions with other molecules, and completely disrupt the native tissue environment. When we look at clinical diagnostics on living patients, techniques like positron emission tomography or PET scans rely on injecting radioactive tracers directly into the patient's bloodstream. This process is not only expensive and highly invasive, but it also offers very limited spatial resolution. You can see general glowing areas of plaque buildup, but you absolutely cannot see the microscopic details of what is actually happening at the cellular level. This is exactly where label-free neuroimaging steps in, to completely sidestep these limitations. Instead of introducing a foreign molecule to light up a target, these advanced optical modalities do something incredibly elegant. They listen to the innate songs of the native molecules themselves. They measure their natural vibrations, their interaction with light, their mass, and their structural density. At the absolute vanguard of this revolution is a suite of optical techniques based on something called Raman scattering. The Raman effect was first described by the brilliant Indian physicist C.V. Raman way back in 1928. Using nothing but sunlight, a narrow photographic filter, and a specialized polarization system, he made a discovery that won him the Nobel Prize. He noticed that when light interacts with matter, the overwhelming majority of the light simply bounces off elastically, meaning the photons keep their original energy. This is called Rayleigh scattering. But about 1 in 10 million photons interacts inelastically with the electron cloud of a molecule. During this ultra-rare interaction, the photon either gives up a tiny quantum of energy to the molecule or takes a tiny amount of energy away from it. This tiny shift in energy corresponds perfectly to the specific vibrational frequency of a chemical bond. If it loses energy, it is called Stokes scattering. If it gains energy from an already vibrating molecule, it is called anti-Stokes scattering. Either way, this energy shift acts as a highly unique, unfakeable fingerprint for absolutely every chemical substance in existence. In the specific context of Alzheimer's disease, Advanced nonlinear Raman techniques, specifically coherent anti-Stokes Raman scattering, known as CARS, and stimulated Raman scattering, known as SRS, have emerged as extraordinary tools for mapping brain pathology. Let us consider the amyloid beta plaque, which is one of the primary pathological hallmarks of Alzheimer's. Traditional biology textbooks will tell you that these plaques are simply aggregates of misfolded proteins. However, when researchers aim an SRS microscope at these plaques, an entirely new, mind-bending dimension of data emerges. By carefully tuning the microscope's laser to the amide I band, which is a specific vibrational mode corresponding to the carbon-oxygen double bonds found in the backbone of proteins, scientists can detect the exact secondary structure of the tissue. Functional healthy proteins in the brain are largely composed of flexible, spiral structures called alpha helices. These act like dynamic springs, allowing the protein to bend and perform its necessary biological functions. But when the amyloid beta protein misfolds and starts to aggregate, it essentially uncoils and adopts a rigid, flat structure known as a beta sheet. These beta sheets are like corrugated cardboard. They stack tightly together, completely squeezing out water molecules and forming impenetrable fibrils that the brain's immune system, specifically the microglia cells, simply cannot break down or clear away. Now here is the magical part of label-free imaging. SRS microscopy can actually detect a distinct blue shift, a shift of approximately 10 inverse centimeters in the amide I spectrum that occurs precisely when proteins transition from flexible alpha helices to rigid, toxic beta sheets. For the very first time in medical history, researchers can rapidly and directly image the spatial distribution of misfolded proteins in a fresh brain slice without using a single drop of chemical dye. They can distinguish diseased tissue from healthy tissue purely by looking at the vibrational frequency of its chemical bonds. But the story, told by label-free imaging, absolutely does not end with proteins alone. For a very long time, the dominant narrative of Alzheimer's disease has been the amyloid cascade hypothesis. This heavily focuses on protein aggregation as the sole root cause of the disease, and for decades, pharmaceutical companies spent billions of dollars targeting these plaques, often with very disappointing clinical results. However, label-free CARS microscopy is shifting the entire paradigm. CARS is uniquely and perfectly suited to imaging lipids by detecting the symmetric stretching vibrations of carbon-hydrogen bonds at very specific frequencies around 2,840 to 2,850 inverse centimeters. When researchers image Alzheimer's brain tissue using CARS, it clearly reveals something that standard protein stains completely missed. It shows that senile plaques are frequently surrounded by massive, dense halos of abnormal lipid accumulations. By analyzing the intensity ratio between different stretching frequencies of the carbon-hydrogen bonds, label-free vibrational imaging can easily distinguish these fatty lesion areas from healthy neural real estate. This direct, entirely undisturbed observation strongly supports a major emerging view in neuroscience. It suggests that Alzheimer's is not just a protein problem, but also a catastrophic breakdown in how brain cells process fats. The human brain is nearly 60% fat by weight. Lipids like cholesterol and phospholipids are incredibly crucial for maintaining the myelin sheaths that insulate our neurons. If localized lipid metabolism fails, the insulation breaks down, causing massive short circuits in neural signaling. Localized lipid dysregulation is not merely a byproduct of Alzheimer's disease, it is a core structural component of its architectural collapse. As we dive even deeper into this microscopic world, Fourier transform infrared spectroscopy paired with Raman mapping has allowed scientists to reconstruct the actual chronological life cycle of an individual amyloid plaque. According to recent label-free infrared imaging studies on human brain tissue, we now know that amyloid plaques undergo a very distinct maturation sequence. In their infancy, they are known as diffuse plaques, which consist of short, loosely packed, anti-parallel beta sheets. These indicate the presence of highly toxic amyloid oligomers drifting around the neurons. As the disease silently progresses over years or even decades, these diffuse structures condense into what are called compact plaques. Eventually, they mature into classic cord plaques that are characterized by massive, highly organized parallel beta sheets, indicative of incredibly dense fibrillar networks. Seeing this entire chronological progression mapped out spatially, entirely without the inherent bias of antibody affinity, provides an unparalleled window into the biophysics of neurodegeneration. Fascinatingly, the application of label-free Raman mapping, utilizing a 532-nanometer excitation laser on human brain tissue, has also unmasked a completely hidden player in the Alzheimer's microenvironment. That hidden player is carotenoids. In normal, non-plaque areas of the brain, these molecules are virtually absent or just randomly dispersed in trace amounts. Yet, right around the dense cores of mature amyloid plaques, label-free imaging detects intense, highly localized spikes in carotenoid signatures. Why is this important? Because carotenoids are intimately linked to oxidative stress and our body's natural antioxidant defense mechanisms. Their highly localized presence essentially acts as a molecular flare gun, suggesting a very specific, intense neuroinflammatory response, directly targeting the misfolded protein accumulations. This kind of holistic microenvironmental mapping is practically impossible to achieve with traditional staining methods. Traditional staining requires researchers to know exactly what they are looking for far in advance. If you do not have a specific chemical stain for carotenoids, you will simply never see them. Label-free techniques, on the other hand, are fundamentally unbiased. They illuminate the entire chemical landscape all at once, allowing the tissue to simply speak for itself and reveal its own secrets. While vibrational spectroscopy dramatically unveils the complex chemical composition of the brain, another absolute marvel of label-free technology has cracked the code of whole-brain, three-dimensional structural mapping. This revolutionary technique is called cryo-micro-optical sectioning tomography, or Cryo-MOST. Traditional histology requires researchers to slice the brain into incredibly thin physical sections, stain them individually, and then attempt to digitally stitch them back together on a computer. This is a painstakingly slow process that is always fraught with mechanical distortion. Tissues tear, stretch, and warp. Cryo-MOST completely circumvents this nightmare by utilizing the natural autofluorescence of amyloid plaques. Autofluorescence happens when naturally occurring compounds in a tissue emit light after absorbing it. Normally, this natural signal is very weak and easily drowned out by background noise. But researchers made an incredible quantum physics discovery. They found that by dropping the brain tissue temperature to below -100 degrees Celsius, the molecules lose almost all of their thermal kinetic energy. Instead of vibrating and losing their absorbed energy as heat, the molecules are forced to release that energy as a much brighter photon of light. This thermal freezing trick dramatically enhances the natural fluorescence of senile plaques, while simultaneously preserving the structural integrity of the tissue perfectly, like a block of ice. An automated, ultra-precise system then incrementally shaves the frozen brain block, capturing massive high-resolution optical images at every single micron of depth. The end result is a breathtaking, three-dimensional, micron-resolution map of the entire brain's amyloid burden, all captured in its native anatomical context, without adding a single exogenous label. This holistic wide-angle view is absolutely vital for pharmaceutical companies trying to evaluate exactly how experimental Alzheimer's drugs distribute themselves and clear plaques across completely different regions of the brain over long periods of time. Moving beyond just bouncing and manipulating photons, mass spectrometry imaging, particularly utilizing high-resolution platforms like Fourier transform ion cyclotron resonance, provides a completely different, but highly complementary, label-free perspective. Instead of shining a light on the tissue, this method uses a highly precise, focused laser to essentially vaporize microscopic grid points across a frozen brain section. The instantly vaporized molecules are then sucked into a massive vacuum chamber within a mass spectrometer, where they are precisely weighed based on their mass-to-charge ratio. This incredibly precise weighing process allows for the simultaneous spatial mapping of hundreds, sometimes thousands, of specific lipids, metabolites, and peptides, all across an Alzheimer's brain section at the exact same time. While standard immunohistochemistry can only target one or two proteins at a time, based purely on antibody availability, mass spectrometry imaging acts as a broadband molecular radar. It can instantly identify incredibly complex, overlapping pathologies. For example, it can show the exact spatial colocalization of specific gangliosides, myelin lipids, and fragmented amyloid proteins right in the middle of a degenerating cerebral cortex. Furthermore, the physical architecture of the brain tissue itself holds massive, largely untapped diagnostic potential. We are talking about its physical density, its refractive index, and the exact way it bends incoming light. The sheer accumulation of neurofibrillary tangles and amyloid plaques fundamentally alters the microscopic optical properties of the brain tissue. Innovative techniques that exploit light phase and polarization, such as quantitative label-free imaging with phase and polarization, or QLIPP, precisely measure the retardance and anisotropy of brain slices. In a healthy brain, normal white matter tracts have a beautifully highly ordered, directional architecture due to the perfect parallel alignment of myelin sheaths and neuronal axons. When Alzheimer's disease ravages these tracts, this beautiful structural order entirely breaks down, and structural entropy wildly increases. Recent studies utilizing learning-based quantum sensing and advanced polarization metrics have shown that the physical structural differences caused by intracellular tau tangles inside the neuron versus extracellular amyloid plaques outside the neuron yield very distinct linear entropy signatures. The sheer physical density and the localized structural disorder of these protein aggregates actually scatter polarized light completely differently than healthy tissue. This allows researchers to clearly discern the severity of the pathology simply by analyzing exactly how the diseased tissue warps passing light. Now, you might be thinking to yourself, how on earth do human researchers make sense of all this incredibly dense, multidimensional data? This massive influx of physical data from label-free optics has actively paved the way for the ultimate technological convergence, the integration of artificial intelligence. When a human researcher looks at a label-free phase image or an autofluorescence scan, the image often just appears as a highly confusing, chaotic grayscale landscape of varying contrasts. It entirely lacks the bright, artificially color-coded certainty of traditional fluorescent dyes. Enter deep learning. Researchers have recently begun training highly sophisticated convolutional neural networks, particularly structures known as 2.5D net architectures, to seamlessly translate these complex label-free physical measurements directly into accurate, colorized molecular descriptions. A standard UNet is an artificial neural network specifically designed for medical image segmentation. It works by shrinking an image down to its core mathematical features to understand the broad context, and then mathematically expanding it back up to pinpoint exactly where those specific microscopic features are located. By utilizing a 2.5D approach, the AI analyzes a stack of adjacent 2D slices. This brilliant trick allows the artificial intelligence to deeply understand what is immediately above and below the specific slice it is looking at, giving it pseudo-3D spatial awareness without requiring the massive, overwhelming computing power needed for true 3D volumetric rendering. By intensely training the AI on thousands upon thousands of paired images, where a piece of tissue was first imaged label-free and then subsequently chemically stained to reveal the actual chemical ground truth, the neural network slowly and systematically learns to recognize the completely invisible physical signatures of specific cellular organelles and protein aggregates. Once it is fully trained, the AI can take a raw, grayscale, label-free image and perfectly predict or computationally generate the exact fluorescent stain on a computer screen. This concept of virtual staining represents the absolute holy grail of histopathology. It means medical professionals can achieve the perfect chemical specificity of a targeted fluorescent dye using only the completely non-destructive, fast, label-free physical measurement of the tissue. The profound implications of this ongoing label-free revolution extend way beyond the isolated academic laboratory bench. They are currently charting a direct course toward real-world clinical and in vivo applications that could save millions of lives. Today, diagnosing Alzheimer's definitively in a living patient still requires either an incredibly costly PET scan, a highly painful and invasive lumbar puncture to carefully assess cerebrospinal fluid, or ultimately a post-mortem brain autopsy when it is obviously far too late to intervene. The absolute dream of modern neurobiology is to detect this horrible disease non-invasively, decades before any real cognitive decline even begins to manifest in a patient's daily life. Currently, cutting-edge label-free techniques like optical coherence tomography and Raman spectroscopy are being aggressively adapted for retinal imaging. You see, the retina at the back of your eye is not just an organ of sight. It is fundamentally an exact extension of your central nervous system, and it shares the exact same embryonic cellular origins with your brain. Multiple long-term studies strongly indicate that amyloid accumulation and microscopic vascular changes actually occur in the retina, directly parallel to their occurrence deep within the cerebral cortex. Because the human eye is optically clear by design, label-free imaging techniques can be easily and painlessly deployed right through the pupil to safely measure the exact molecular and structural health of the retinal layers in living patients. This incredible breakthrough could very well offer a simple, routine, entirely non-invasive screening tool for early-stage Alzheimer's disease that you could get in just a few minutes at a normal annual eye doctor appointment. Furthermore, the rapid miniaturization of multiphoton and nonlinear optical systems into tiny coherent anti-Stokes Raman scattering microendoscopes is rapidly paving the way for revolutionary intraoperative tools in active surgery. While currently primarily explored for brain tumor margin detection to help surgeons know exactly where to cut, the ability to effortlessly maneuver a microscopic fiber optic probe deep into living brain tissue to obtain real-time, label-free histological images could utterly transform how neurodegenerative diseases are monitored and treated in the future. A highly trained surgeon or clinician equipped with a stimulated Raman scattering probe could instantly determine the exact chemical composition of the tissue right in front of them in absolute real time. They could flawlessly differentiate between healthy lipids, toxic amyloid fibers, and structural collagen instantly on a monitor in the operating room, without waiting agonizing days for a remote pathology lab to fix, section, and physically stain a tiny biopsy sample. The massive transition to label-free neuroimaging is not merely a fancy technological upgrade. It is a profound, philosophical evolution in the life sciences. For centuries, our foundational understanding of biology has been inherently destructive. We kill, fix, freeze, slice, and heavily stain living tissue just to understand it. In doing so, we so often end up studying an artificial artifact of our own clumsy creation rather than the actual, living biological reality. Alzheimer's disease, with its incredibly delicate interplay of misfolded proteins, shifting lipid metabolism, and highly localized neuroinflammation, simply demands to be understood in its native, completely unperturbed physiological context. By harnessing the subtle, beautiful physics of light, the inelastic scattering of photons, the precise generation of harmonic frequencies, the measurement of quantum anisotropy, and the seamless translation of these complex physical phenomena through the immense power of artificial intelligence, we are finally learning to truly observe the delicate human brain without altering it. We are carefully listening to the tiny vibrational frequencies of the amide bonds. We are carefully mapping the intricate lipid halos surrounding senile plaques. We are tracking the exact structural evolution of amyloid, from a tiny soluble oligomer all the way to a massive intractable fibril. We are mapping the true molecular architecture of Alzheimer's disease in its absolute purest, most native form. And in this pristine, beautifully clear, label-free clarity, we may very well finally find the exact molecular insights critically needed to completely dismantle the devastating architecture of the disease itself. Thank you so much for tuning in to G Fun Facts Online. We hope you learned something fascinating today about the cutting edge of neuroscience, and we will catch you in the next one.